You don't actually have ownership of R at this point, you only have R one step later. Okay, and why do we have this? Why does this show up in this logic and not in many other separation logics before? It's because the invariants in Iris are so-called impredicative invariants, meaning that R here can be anything, right? This could be any assertion of the logic, including an assertion which mentions the existence of other invariants, okay? It can be a complete, and this cyclic nature of the construction of the model of assertions means that the only way to solve that is to use step indexing. And so how does this affect proofs? Okay, so here's just a very simple example of what happens. So you have here this is just a load of L. I'm using ML notation here. So we're doing a load of L, and in a context where we have this invariant that says at all times exists n, L points to n. So how do you do this? Well, you use the invariant rule. You open it up. You get later of exists n, L points to n in your precondition, and you have to restore it in the post. And now you still want to, you need to actually get that L points to some particular n in order to prove bang this Hoare triple for bang L. So you need to somehow get rid of that later. Okay, that's the name of the game. And this is what we call the later elimination problem. We have later R in our context. We need the underlying R in order to proceed with the proof. So there are various options for how you can deal with this. And they work one of them at least works most of the time. So one of them that's very commonly used is so-called timeless propositions. So the idea here is that there's a significant class of propositions in Iris which are basically like the sort of first order propositions, which are called timeless because the model of those propositions does not care about step indexing at all. And so for these propositions, which includes, by the way, the points to connective and a variety of other connectives, you can simply strip off the later. You can just drop it because it doesn't. The meaning of the assertion doesn't care about step indexing. There's also a bunch of commuting rules. So often you get later over a big invariant, and you have to push the later down into the assertion, and later commutes with most of the connectives of the logic. And then also, if you take a step of execution, so if I step E to some E prime, then if I have any later assumptions in my precondition, I can just strip off the later. Okay, and that's because step indexing is indeed tied to, by the model of the Hoare triple, is tied to steps of computation. So that's all good. And so as I said, these existing options do apply to most invariants. So for the example that I showed before where we had the invariant exists n, L points to n, that's a timeless proposition. So you can just strip off the later and do the proof as you would ordinarily do in any other concurrent separation logic. But it's not a silver bullet. Okay, so I think of a very simple example, for sort of the canonical example of where this breaks down. Suppose I have a nested invariant. So an invariant whose contents are an invariant that says exists n, L points to n. We can question why you would do this in a second, but let's just suppose you do, because invariants are impredicative. You can put arbitrary assertions in there, so why not? The problem is, of course, that when you open this invariant, you get something which is not timeless, and so you can't strip the later off of this. So if you did this in a proof, you would just basically get stuck at this point. You can't do anything more with a later of an invariant. You can't open that in this same step of execution. So what do? Well, you cry for help. Okay. So first of all, I mean, you might say, sorry, before I get to that, you might say, why do you care about this, Derek? Really? I mean, who's writing invariants that contain invariants inside them? And for that, I can't completely dismiss that criticism right at this moment, but you'll have to take it on faith that, in fact, this is representative of patterns that arise naturally when you're working in a higher order logic like Iris. You just naturally get invariants that talk about arbitrary other propositions which may contain, for example, invariant assertions in them. So this does arise in practice, even if this particular example is not what you would write. The second point, though, is that often when people start using Iris, they naturally get into a state where, I mean, they're told that you can put anything in invariant. So if you can put anything in invariant, why not have an invariant inside an invariant? And so this sort of becomes a hindrance to the usability of the logic. So this was actually what happened with my student Simon, who's the first author on this work. He started working on Iris, in the first couple weeks of working on Iris, he naturally, just because he was playing around with it, started to use nested invariants. And so he cried for help on the Iris help desk on Mattermost. And he got very helpful answers, and basically they were of the form, well, have you tried doing a non-local refactoring of your entire proof where you flatten your invariant hierarchy so you don't use nested invariants? Or potentially just give up and work on some other problem. And so this is typically in the past been the answer is sort of don't do nested invariants. It's not a good idea. Try to figure out how to make these sort of more global changes to your proof strategy. But this is kind of a sad answer because the whole point of Iris is you can actually do these arbitrary higher order constructions. So then to say, well, the first time you try to do one, you fail, is very disappointing. So what about another option? What about using the fact that we're working in a separation logic to help us solve a problem in our separation logic with step indexing? So this is what later credits, where later credits come in. So basically later credits, the basic idea of later credits in one slide is that we have this problem, we want to eliminate laters. So let's think of that as a right. Turn the right to eliminate a later. In other words, the ability to transform later R, to strip off the later, into an ownable resource, which we're going to represent as something called a later credit, denoted appropriately given our current location with the pound sign. Once you do that, then you can manipulate that resource just as you do anything else in separation logic using all the full mechanisms of separation logic. You can pass these resources around from thread to thread. You can frame them around function calls. You can share them using invariants. And this can solve a lot of the problems that naturally arise with later reasoning. So here's the later credits in one slide. The basic idea is very simple, right? Here I showed this rule before that if you take a step of computation, you can strip off laters from anything in your precondition. Well, and by the way, this will work for other things, not just pure steps, but I'm just showing a simplified version here. The idea here is we split this in two. So when you take a step of computation, you don't immediately strip off the later. You instead get a later credit, which is the right to strip off laters at a later point in time. And then you have a separate rule which says if I have a later credit in my precondition and I have a proposition with a later in front of it, R, I can strip off the later. That's it. So we're just separating those two things, those two aspects of the later elimination that was already present in Iris. And what does this buy you? It buys you a kind of prepaid or amortized reasoning about later elimination. So, for example, suppose you have this expression here where we're trying to verify f applied to, this is just a contrived example, but just to give you the point, the basic idea, f applied to 41 plus 1, and then you read from L. When you execute 41 plus 1, that takes a step of computation. So when you do that, you can obtain a later credit, which you can then freely use later on when you verify the load of L. So concretely, you have that first step here where you execute the 41 plus 1 and you get a later credit when you move to 42. Then of course you can frame that later credit around the function call to f of 42. You still keep it around. And now at the point where we actually are verifying the load, even though we have a nested invariant here, we first apply the invariant rule. We get later around the inner invariant. But we still have this later credit around from when we executed 41 plus 1. So at this point, we can simply spend our credit, strip off the later, and we're good to go, and proof is as usual. Okay. So this is really, this is in some sense a very familiar concept in programming languages and computer science of amortized reasoning, but here enabled by the presence of, by working in a resource logic, like separation logic. So let me give you, so there's actually a number of examples where this is useful. I'm going to give you, starting with a very simple one that I found particularly surprising, which is going back to this invariant rule in the first, the invariant rule I showed you at the very beginning, and seeing if we can do better than what Iris is giving you. So remember this rule that I showed at the beginning. This is sort of the rule that was on page 1 of the Iris 1.0 paper. And there was no laters anywhere, all right? Given how annoying it is to deal with laters and eliminating them, wouldn't it be nice to just remove it, right? Just have this rule. And so this is something that Simon asked me early on, was like when he was studying Iris, was, do we really need this? Is this necessary for soundness? And I said, yeah, I think so. It's the model of step indexing dictates that you have to have a later there. So of course we have to have the later there. And we have all these paradoxes which are sort of look like this, that say if you don't have the later, then something goes wrong. But they're not exactly this, so I'm not sure. So it turns out you don't need the laters. So the idea is you simply define an alternative version of the invariant mechanism, the invariant assertion, here written with this pre thing, which is basically a prepaid invariant. It says not only does the invariant store R, but it stores a later credit that has been prepaid so that when the invariant is open, the later on the R can be removed. So then you see, for example, when you use this, you get what you'll get in your context is later of R star later credit. The later credit is timeless, so you can strip the later off the later credit and then pay for the elimination of the later, so you just get R here. Now you'll notice here in this simplified example here, you still have to restore R star later credit at the end. And so you might say, well, that's a little annoying that these later credits are popping up in something as basic as the invariant rule. But it turns out that, I mean, it's not a big deal because this will be generated by the step of computation. But still, you can actually, by extending the later credits mechanism and generating more than one later credit per step, which I'm not going to show you how that works, but this is another technical trick, we can actually get this rule that we wanted in the beginning with no laters whatsoever. Right? And for me, this was totally mind-blowing. As someone who was sort of, the necessity of these laters in this basic rule of the logic was something I had assumed for many years. So I was very impressed. But you might say, okay, well, that's very nice. That's very nice. But in practice, are there other examples that are useful? And there are. So I'm not going to talk in detail about this, but I just wanted to briefly mention there's this thing called unsolicited helping. So basically, one of the calling cards of Iris is its support for proving logical atomicity, which is inspired closely by the previous work on Tada. And one of the nice things about logical atomicity, proving logical atomicity, by the way, this is kind of like a linearizability-like property, but internalized within the logic. One of the nice things about logical atomicity in Iris is that this has worked from the beginning, even for proving this for fine-grained concurrent algorithms that exhibit this feature called helping. I don't know how many of you are fine-grained concurrent algorithm geeks who know about helping, but basically it's where the thread that wants to do a certain operation is not the one that actually has the linearization point of that operation in its code. The linearization point happens in some other thread, which is called the helper thread. So that was something very good about Iris from the beginning, but it failed to cleanly handle a certain class of algorithms. They're not super common, but they do come up, which have this feature called unsolicited, or what we call unsolicited helping, which is basically where the helpee doesn't actually, the thread that needs to have its linearization point committed, doesn't ever explicitly communicate with the helping thread. And so what happens is basically the helping thread gets to the point where it needs to commit a bunch of linearization points for other threads, and those the ghost updates that are sort of needed to commit those linearization points are under a later, and it can't do it. And so, as you could probably guess, this idea of prepaid later elimination with later credits saves the day here, because each helpee thread, the one that wants its linearization point committed, simply has to contribute a later credit up front, put that in the invariant that is shared with the helping thread. And then that way, when the helper wants to commit all the linearization points for the other operations, it has the later credits it needs to simply strip off the laters from their atomic update operations, and then it can complete the proof. So this sounds a bit obscure, perhaps, but this is actually already used since later credits were developed 2 years ago. This has already been used in a couple systems verification papers that the MIT Iris users. It's a variety of people, but working with, especially with Franz Kashuk and Nikolai Zeldovich and their group that they published last year in OSDI and SOSP. So these are, it's sort of funny to think about a paper that, or some idea that is applying separation logic to improving step indexing is somehow making it into systems verification papers. But this just, I think, goes to show yet another example of the power, the unexpected power of separation logic. That this can come up, that you can have problems like step indexing, which I would never have thought would have anything to do with separation logic, and yet sort of basic problems with reasoning about these kind of models are addressed very nicely with this basic idea of separation logic. And for that, I have to deeply thank Peter and his many collaborators, of course, and I want to wish you a happy birthday. Thank you.
So we will have a time for maybe one or two questions. Peter, yeah.
That's very interesting. So suppose your programming language wasn't concurrent. Maybe it's the sequential subset of ML or pure untyped lambda calculus. You can model that using, these recursive domain equations and solve it with step indexing. Do the problems of reasoning about it, the same problems arise there, and do later credits help there? I mean, does it depend? Concurrency gives us loads of examples. Is the technical problem related to the concurrency?
I mean, it's not fundamentally, well, okay. It's a good question. I don't know. Do we have, I'm looking at Simon now. Do we have examples where it's useful not in a concurrent setting?
I think a lot of the examples are just like convenience things where you
But,
could do
yeah.
a more complicated proof, but because you can apply it in a sequential setting, you just collect a bunch of later credits, and then later on when you face a bunch of laters, you just use them.
Right. But still, you're working in a language where you have something like the invariant rule. Like, I mean, most of our examples involve, most of our applications involve concurrency in some way. I don't know that it's fundamental. I mean, for example, step indexing is useful even in the sequential set. In fact, where I started using separation logic to begin with was in building a model of a sequential higher order stateful language. Basically an ML-like non-concurrent language, and where you still want to have invariants on private state that are preserved across, in the presence of reentrancy and things like this. So it was still useful there. Whether later credits are specifically, it's again one of these things. Is it needed? I don't know. Would it be useful? We haven't looked at such examples.
Do you use the later modality when
you use those models? Yes. Later modality is useful independently of concurrency, and that's where we started with.
Okay, so let's thank the speaker.